Now we can look at multi-stage games. And multi-stage is different because there's timing here. There's a sequence rather than all at one time, and simultaneously there's a time frame involved. So we call these an extensive form game. And that's where players have information. We know the outcomes and we know the strategy. We know the sequence of who goes first and second, and therefore that characterizes an extensive form game. So here's an example of a sequential move where we have two parties, A and B, and A goes first. So A says, I'll go up, and B will say, I'll go up or down based on whatever is chosen by A. So they could have the benefit of watching. So B will then look at A's move. In this example here, if A says, I'll go down, then B will look at, should I also go down and therefore receive a reward of 20, or should I go up, in which case we get 0. So the choice that B would make if A had already made the move of going down is pretty clearly to also go down, because in that scenario, B would get 20 compared to getting 0 if they went up. So this is a Nash equilibrium that exists for A going down. B would also go down to be at a point of 6 and 20, because neither party wants to go to 0. So both are happy with their respective 6 and 20. This next scenario is, what if A announces going up? Well, if A announces going up, then B says, okay, if I go up, I get 15. If I go down, I'll get 5. Therefore, I'll go up. So again, in that case, it's another Nash equilibrium, because neither party would want to deviate from 10 and 15. If A were to deviate at that point, they would drop to 5. If B were to deviate, they would also drop to 5. So both would be happy to accept the 10 and 15. Now notice that that's also better overall, that 10 and 15 is better than 6 and 20. There's a different equilibrium here called a subgame perfect equilibrium. And this looks at a set of strategies where there's Nash equilibrium, but also allows no player to improve their position by changing strategies. So here we have a subgame perfect equilibrium. A choosing up leads B to choose up, and that makes a higher playoff. Just going back to the example. It does no good for A to choose down, because when A chooses down, they know what B is going to do, and A will end up with 6. And they also know the other side is if they choose up, B will choose up, and they make 10. So there is an optimal move here, and that is in this subgame scenario. A is going to choose up because they can predict that B goes up, and that's the perfect equilibrium for them. So that's a perfect subgame equilibrium for A, to choose up because we're forcing the hand of B to also go up, which means A will make 10. Let's do a different scenario. Let's do an entry game where A is a company considering a move into a new market that is currently dominated by B. If A chooses not to go into the market, then B gets all the money and makes 10. However, A can enter the market and B will threaten like crazy that they're going to go hard with a response so that A will regret it, and that response will lead to the endpoint of A losing money. Let's call it $1 million because a dollar doesn't sound interesting. So B is essentially threatening A, if you enter, I'll go hard against you and you lose $1 million. However, if you look at the outcomes, B's choices as follows. They can go hard against A and A would lose 1, but B would only make 1. However, if they made room for the market and B went with a soft response, then true, A would get 5, but B is going to end up with 5. If A announces the entry into the market of B, if B thinks A is serious about it, they're going to go soft, because to go hard against A committed entrant, they're going to actually go down from 10, which is their monopolistic position, down to 1. Whereas if they do a soft response, they'll go from 10 down to 5. So this is the subgame perfect equilibrium for A, since by announcing going in, it will force the hand of B into going soft, and therefore A will make 5. So let's summarize chapter 10. We looked at the game theory basics. What is game theory? What are the components that need to be specified? Is it simultaneous or sequential in terms of the moves made by the various participants? And is it one shot or is it repeated? Then we looked more closely at the scenario of simultaneous move one-shot games. And this is where we define what is a dominant strategy for a participant, what is the secure strategy, and what is a Nash equilibrium. We applied it to 4 different scenarios. One is pricing, the next is advertising strategy, the third is coordination decisions, and the fourth is monitoring of employees. Then we looked at the scenario now of repeated games as opposed to one shot. There is an incentive for collusion. Even though there may be a Nash equilibrium, the incentive for collusion still exists. However, there would likely be a triggering mechanism, since it is a multi-period game, such that if there is a cheat or a reneging by one party, the other party can then exact a punishment on the party that perpetrated the cheat. And that is the scenario of a collusion that breaks down back into a Nash equilibrium. Next, we looked at finite repeated games, where there is a known or unknown end period. And we see that there is a different behavior under each. 2 applications that we did for this finite repeated game is resignation or quitting by an employee. In that case, management will try to maintain a punishment weapon, and that punishment is future benefit from a graceful exit from the firm. And that could take the form of recommendation letters or referrals or even rehiring. Then there's this scenario of a snake oil salesman, where if this salesman comes in, makes all the promises now, knowing that if they sell a product, they can leave town, and therefore promises have no meaning because whatever it takes to get the sale. It's quite different if the salesman stays in town, where the punishment is substantial and effective, where if the reviews are terrible, there's no further sales in that city. So if the salesman wants to stay in that city, he can't lie and say anything just to get a sale because there's a consequence for it. And our last stop was looking at multi-stage games with a sequence where A makes a move, B sees the move, and then considers the outcomes, and then makes a move for B. In that scenario, we see that there are Nash equilibria in that scenario, but we also see the possibility of a subgame perfect equilibrium, where we can almost dictate the end result based on our move and our prediction of what the other party will do given the choices, now that the choices have been constrained. So that's what we see in a sequential multi-stage game. All right, that's it for chapter 10. I'll see you for chapter 11.